The next presentation will be presented by Mr. Hyfandí, and the subject is desalination of renewable brackish water sources in coastal areas, the case of Almiros, Heraklion, Crete.
Hello, everybody. Okay, I would like to present you a case study. I'm Dr. Alexandra's Hyfandí from SYCHEM group of companies, and I would like to present you an actual study that we have made for the meaning of the desalination for renewable brackish waters. So it was extremely interesting to hear before the keynote speaker to discuss about karstic formations and the water, and that of course there is water hidden actually in aquifers that we don't know. And this water is very important because we can use it and we can make it drinkable in a very low cost. And this is the aspect of my presentation. So first of all, everybody, we know about the water scarcity. We know that it is a very common phenomenon in several areas of the world due to natural reasons. It's also an exponential phenomenon due to the climate change and the increase of the human population. So we all know that desalination has a key role against water scarcity. And why is this? Because desalination can offer a reliable source independent of the climate change. 71%, everybody we know, of the Earth's surface is water covered, and the oceans hold about 96.5% of all Earth's water. And we know also, of course, that coastal areas are the most inhabited areas and they have the biggest growth. We know also that the main desalination technology, reverse osmosis, needs only electricity as power. So there is no carbon dioxide emissions if we use renewable energy sources. So in principle, we can produce as much water as we want, as long as we have the energy to produce it. And the recent development of technology in reverse osmosis drastically reduced this cost. So desalination in general is a sustainable technology for potable water production. But what is the challenge? The challenge for seawater desalination plants is exactly the problem of energy. Today, the cost of a desalinated water, it's competitive for potable water, but it's really non-competitive for agricultural needs. And the open seawater intake is a major issue in terms of CAPEX and OPEX. So we're discussing something between 0.6 and 1.5 euro per cubic meter. You can see this big deviation because it depends on the size of the project. But still, for agricultural water, we need to reach values below 0.2, even 0.1. So this is away from any possibility right now from the seawater. But we have a new source, which is very, very underestimated. The people in the past, they knew these sources. It was, we call them, in Greece, we call them glyphs. I will tell it in Greek also. That means that there was a little bit of brackish water coming out near the coast, and it was crazy because this water was flowing all the time, even in the summer, in a very shallow wells. But what was this water actually? From where this water is coming from? This water is actually a renewable water. It is water that is coming from karstic formations in the mainland that is finding some ways to go out, and actually before entering in the sea, it's already mixing with the seawater. So this is why it's becoming brackish. So this brackish water is not a water that it's really this water is not a water that became brackish because of exploitation of the hydrophore. It is a naturally brackish water. It is actually a sweet water, but we will lose it in the sea because this water is ending up in the sea. It is waste. It is a natural water that is moving to the sea, not from rivers, but from karstic formations. So this is the meaning of the renewable brackish water. And let's go to the technology now. let's talk about desalination. Why the desalination of renewable brackish water is the best practice. First of all, because the required pressure to produce the water is 65 to 85 less than the seawater. The capex is 70% less. It is extremely efficient and cost-effective way to produce water, even to agricultural use. Very, very important environmental effects. There is no brine. The big problem of desalination is the brine. There is no brine. Because when you treat the brackish water, the salinity of the condensate, is not brine anymore, is less than the seawater. So you can throw this condensate in the sea without any problem. The brackish water will finally go to the sea. So you are not destroying the hydrophore. You are using actually water that is going to the sea. It is not going through a river, but is going through a karstic formation. And it is hidden. And all this year is not really used so much. So there is no environmental effect. Of course, there are some restrictions. The first one is the quantity. And the second is that we need to allocate. And this is the role of hydrogeology. And this is why very important the previous speaker to discuss about all these modern techniques to allocate where this water is going, because it is very difficult. You allocate it by chance. You allocate it by people in the past that they know where this water was, because they had made some drillings. So, in Greece now, as you can see, 22% of the water produced from desalinations in Greece is already brackish. And 35% of the plants is in the region of Crete. Why? Well, we are going now to the amazing example of the Almiro Spring, which is a unique system. It is a special system. It's flowing all the day, all the year, and the salinity is starting from 500 microsiemens and go up to 8,000 ppm, and they go up to 8,000 ppm. This is a tremendous change, and that is because it's an amazing karstic phenomenon. It's coming from the mountain, but then in the mountain, the seawater is meeting the fresh water, and actually is going out to the spring, which is very close to the sea. It's only something like 500 meters away from the sea, and it's coming out brackish. But now, so see the number, 250 million cubic meters. Approximately 50% of all the water of Crete is going out from this spring. And this spring, until 6-7 years ago, it was completely unexploited. The first exploitation is what I'm presenting you here. I'm giving you some amazing numbers also just to understand what's going on. We are discussing that every hour, even in the summer, we have 15 to 30,000 cubic meters per hour going to the sea. The whole city of Heraklion, the fourth biggest city in Greece, they need 40,000 per day. Per day, okay? So, and why this is happening? Because of the karstic formation of Crete. The water in the mountain is going to karstic formations, and these karstic formations are going out. And you can see what is happening. Huge flows in the winter months, and then you can see that the karstic formations, the water is going out the whole year. This flow you can see there is 15,000 in the summer. It is actually 20,000 cubic meters per hour, okay? And you can see what is happening, that as the flow is going out, you can see that the chloride content, the conductivity is going up. So you can see that every month, this water is becoming more and more brackish as the power of the hydrophore is becoming less and less until you have the new rain season. This is the desalination plant. It is 2,000 cubic meters per day. That was actually a small plant, a pilot plant. And it's already expanded to another 3,000, so it is 5,500 cubic meters per day. It's nothing. It could easily produce 30 or 40,000. You can see our company was manufacturing this plant. We also made an artificial source of water so people can drink the water. But the most amazing that everybody should hear and everybody should learn, this is the real cost right now. This is a contract for 10 years. It is 0.16 euro per cubic meter plus 1 kilowatt hour per cubic meter. 0.60 is the operation for 10 years, okay? With a PV cost of 0.02, you can understand that this is 0.18. If this plant is something like 20 or 30,000 cubic meters, we can produce water with 0.1 euros per cubic meter. This water is sustainable for agriculture. And what is the challenge? We need to find and allocate these sources. And I think this is the main, it is a very good scientific field for all the hydrogeologists, that we have to prepare studies and identify where this water, we can find this water. And when we find this water, with a very, very low cost, we can make a reverse osmosis plant, smaller reverse osmosis plant. You don't need huge ones. You can find all these allocations. I can tell you, sirs, here from that you are in Cyprus, Limassol is full of this water. Why you don't use it? No, you made a seawater plant. It is full of this water. You have small rivers going all in Limassol. It's the same in Heraklion. You have 3 rivers like that in all Heraklion. Heraklion was starving for water. It was the only city in Athens, the 4th biggest city, that 3 or 4 years ago it was still without continuous water flow. It is unbelievable. And why? Because the water is going below your feet and is going out to the sea, and you can catch it with a very low cost and make it potable. And you don't need the huge investments with the seawater desalination plants. You don't need the big plants. You only need cleverly designed smaller plants allocated where this water is. And guess also what? This water is very close to where you need it, so you don't need to transfer this water, which is another huge cost. So from an environmental point of view, this is the future. Find this water, this brackish water, this renewable brackish water, and exploit it with reverse osmosis. And this is the cheapest way to produce potable water. So the island of Crete has not only one, but more than 4 actually. We're discussing about 2, but there are another 4 at least major, and hundreds of smallers. The same is happening in Cyprus, but we need to work on it. It's not so easy. So well-designed, decentralized reverse osmosis plants close to the areas where the water will be consumed in combination with small dams or reservoirs to handle the summer peak. This is the sustainable future for water scarcity and climate change in the Mediterranean coastal areas. Thank you for your attention.
Thank you, Dr. Hyfandis, for the very interesting presentation. Do we have any question from the audience? Can I ask you one?
Yes, thank you.
Question. Actually, concerning Heraklion city, do you think that now that we have the dam, the Paselemi dam, do we actually need a desalination plant there, or is it?
This is a tricky question. The dam was designed 30 years ago. It costs 350 million euro to produce, if 30,000 cubic meters per day. To exploit ALMYROS, you need 10 million, and the cost of the dam right now, the dam is selling the water to the municipality for operational reasons, 0.19. This is the cost that the dam is providing water to the municipality, not directly to the authority. So as your authorities here in Cyprus, they are selling the water. So if you ask me, yes, it was crazy that we made the dam. It was the dumbest decision, because this decision was made 30 years ago. Of course, 30 years ago, the right solution was the dam. 30 years after, it was a completely wrong decision that it was made. But it was designed. For years, they tried to find the money. Everybody knows about ALMYROS, you know. Everybody was talking about that. But it should be an example. Some people, they say, oh, it will be €1 per cubic meter, but it's 0.16. So the answer is that now, and our proposal, because as you said, the Aposellemis dam is there. First of all, we all know that in some years, there will be seasons that you will not have. And what you will do? No water again? You know that there will be a time that this dam will not be able. The second is that you have a lot of needs in agriculture. So the question now is that you have to exploit both of them. The dam, that's already there, you pay for it, you have to use it, of course, and you have to strategically exploit all these sources. Because finally, the water from these sources, amazing or not, is even cheaper from operational point of view. It seems amazing to you, but I'm just telling you about real prices right now. I'm not discussing about rumors. 0.19 euros per cubic meter, this is the price of the Aposelemis dam. 0.16 for 10 years, plus 1 kilowatt hours that now it will be, so it is 0.18 right now because we have also the photovoltaic next to it. 0.18 is the cost of the brackish water. The dam is 80 kilometers away. The Almiros is 7 kilometers away from Heraklion. So it's next to Heraklion, actually. Next to where is, so if you ask me, and that's why I say we are not against the dams, but we need to make a completely different approach right now. We need the dams, small dams, not huge dams, together with desalination plants, and we need a lot of desalination plants. We have to go away from this idea, as you have here in Cyprus, huge plants located in 2 or 3 areas. Why? There is no reason about that. Everybody knows that sustainability is all about decentralization. And these brackish waters are completely decentralized. And with very easy, like with this, with containers, you can make small, flexible reverse osmosis plants that you can also operate or non-operate. You don't need huge investments. You don't need to go in the sea. You don't want to make all this infrastructure. Thank you.
Thank you very much. Thank you.
Sorry for just for a moment. I would like to ask you if can you analyze the price? I mean, 0.16 euros per cubic meter. Okay. I'm asking about the. It's out of order. Okay. I would like to ask you about the cost of the 0.16 euros per cubic meter. Does it include the cost of electricity power? Does it include? You said no, I think.
No, but 0.16 is a closed price, including everything: manpower, chemicals, service, is whatever.
The cost
except
the cost of construction of the plant. Mm-hmm. Does it include it? Does it?
No, it's not included.
Oh. Mm-hmm. So it's not 0.16. Mm-hmm. It's much more.
No, let me. It is a
because after 10 years. Mm-hmm. We need to reconstruct.
No. This plant is for more than 30 years, okay. and it's already operating 8 years, and it will be a new contract to operate the same plant for another 10 or 15 years. Okay, so the plant is not. It will not be out of fashion, let's say, or it will need to be completely reconstructed. It is not a seawater plant. So it is constructed from materials for seawater. That means that if you go today, 8 years after, to see the plant, is like yesterday. And the plant has no difference in efficiency. It is not, don't compare it with a seawater plant. A seawater plant is working in 60 bars pressure, 65, and has a lot of problems because of how it is getting the water, filters, a lot of materials, and of course the seawater, which is very difficult. The brackish water plant is a completely different story. It is 1/3 of the price to construct it, 1/4 sometimes, and it is also much less to operate. One more thing, it is a 2,000 cubic meter plant per day. If you make a plant like that of 20,000, the price will be half, because the most of the operational cost is the manpower here. In 0.16, a big cost, huge part of the cost, 30%, is the manpower. And the manpower is the same if you have a 2,000 plant or if you have
So we have
15.
to build another dam in order to. Okay. The time is over, so we'll stop.
But in any case, the capex, just to answer to you, the capex, as I told you, if you want to make a plant like that for 30,000 cubic meters, the capex is 10 million. So I'm answering. If you put it in the 30 years, the price is negligible in the.
Thank you very much. Let's continue.
Yes.